Hi everybody, today we'll be doing Just Green Enough. This one's probably the hardest of the bunch. I had a lot of time struggling and trying to understand the editorial, but nevertheless, it is pretty interesting. Yeah, so let's just go for it. Basically, I'm given a kind of grid, n by n grid, or kind of just set of numbers actually, or yeah, a matrix would be a good example. And what's going to happen is, let me just 200, 150, 200, 150, 2, 141, and 1 through 5. And so what's important is you want to find the number of subgrids that have a minimum equal to 100. So in this case, there would be 8. So actually, this is not a subgrid because it has a minimum of 57, but there's 8. So there's 1 here. There's 4 actually. 1, 2, 3, 4. 100 by itself. Here's another actually, my bad. Here's another subgrid. Here's another subgrid. Here's another subgrid. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So those are the 8, and it can get really messy real quick. When I was trying to make like test cases and all that, I had a lot of trouble like counting and all that stuff, and it was just like, I'm wasting my time at this point. What's going on? So this involves a subsection of mathematics known as combinatorics. So if you're not aware of that stuff and like some tricks to it, this is going to be a very hard problem for you. I recently started doing more combinatorics, which is kind of crazy, but I don't really mind. So yeah, this is how, yeah. So the first idea that I came up with was to have like a quadruple for loop. So the for loop would be like, the first for loop would be for, let's say like I would go to 0 to maybe like, yeah, we'll go to n, j will go to 0 to n. So this would be the first index. And then I would have the length and the width of it. So it would be actually 0 n minus, or actually it would be, I think the length would be kind of j, or the height. That's the height. My bad. That's height. Be I. Wait, no. It would be 0 to n minus I. I think maybe even plus 1. I don't know, but there should be some n minus j. And somehow I would do like, yeah, I would just calculate every single one, brute force it, because brute force is always the answer, if you know what I mean. And maybe do some like O of 1 query to somehow figure out like 2D minimum really quickly. And so I was like, hey, how do you do this? And so I looked at like n, right? Because that's always like a good way to calculate. And it says it's at max 500. So I was like, okay, 500. 500 to the power of 4, because you do it 4 times, maybe get a query out of that. And oh by golly, it is 3. Yeah, it's really slow. And so even with like, I think it gave you like 200, right? If you want to satisfy the first 4, that's still slow. That's like almost 1/10 to the 9. But like technically, if I was doing the contest and I solved problem 1 and 2, I think I would have, but maybe not. And I just solved this, I think I would have like gotten and passed the gold, but like still, this is like ridiculously tricky. So I was like, okay, maybe there's some sort of greedy algorithm with it. Maybe I can like see a pattern. And I was like, okay, I noticed that if you go left, you go 1, and I count the number on the left, so then L will be the number of people greater than 100, right, to the left of it. and R would be the people to the right of it. And I was like, okay, yeah. And then the total amount would be like L plus R plus L times R. There's like a formula for that. That's like kind of the number of combinations. And I was like, yeah, that could work. That could work. It would be like 1 plus 1 plus 1, that's 3. So there's one combination here, one combination there. That's kind of the idea. And I was like, okay, maybe that can work. And then I was like, oh shoot, what if there's like 100 here, and like they start mixing and matching and all that stuff like that. And I was like, shoot, how am I gonna do this, dude? And so the solution to the editorial was what they call complementary counting. It's kind of a probability thing where you kind of count what's opposite. So instead of counting the number, or yeah, instead of counting the numbers that are greater than 100, maybe count the number of rectangles that are less than 100, like with a minimum less than 100. So maybe this would count as well. Now, in this case, they don't really do that. What they do is they count the number of subrectangles that are greater than or equal to 101. And this may sound really weird, but the idea is if you have like multiple hundreds, right? You don't, or yeah, you count the number of subrectangles that are greater than 101, and then you subtract that number from the number of rectangles that are greater than 100. And in doing so, you could get rid of like these lone numbers. And you'll notice what this means later on. But this helps for like tackle the multiple hundreds and like all that stuff. Now here's another issue. This is in 2D. It's gonna be pretty complicated and it's gonna be pretty weird. So what I'm gonna do is I'm gonna break this into 2 parts, right? So one is gonna be 2D, the issue of tackling 2D. The second would be tackling double counting. So when I mean double counting is like counting subrectangles twice because there's multiple hundreds. So let's do 2D first. So a good way to like simplify everything is to make it 1D So let's just like take this, maybe 100, and I'm also going to simplify it further actually. Instead of having different numbers or multiples of numbers and stuff like that, like 114, I'm just going to have hundreds and zeros. All right, so I'm just going to have a group of hundreds and zeros, and I'm just going to plop them all down into one nice little 1D array. And so I'll just make commas because it may be a little confusing. And so let's ask the question, how many subrectangles are that have a minimum of 100? And so, yeah, how many are there? Well, we see 1 here. We see 5 actually that are length 1. We see 2 more that are length 2 and 1 length 3. And so in total, there are, wow, that was like a voice crack. In total, there are 8 different little guys right here. Or, yeah, 8 different. So, yeah. I wish I had like a smart eraser. Can I have a smart eraser? Insert menu. No, whatever. I don't really care. But yeah, I'm just gonna have to undo this. But like there's a pattern here, and so in order to calculate it, so you want to find the length of the segment. So like yeah, first things first, you'll notice that like every segment produces a lot of hundreds, like because it goes through pairs and triplets and quadruplets and all that. And so basically you want to find these segments, and this is a segment length 1, segment length 3, segment length 1, and every time your answer increases by the length of the segment, which would be L in this case, plus or L times L plus 1 divided by 2. If you don't know this form, it's not plus equals, it's or plus or minus, it's plus equals. And if you don't know this formula, this is the sum of consecutive numbers from 1 to L or 1 to N. That's usually what it's used for. But yeah. And this is because you have three. So, okay. Yeah. This is because you have one segment of length L, two segments of length L minus 1, and then dot, dot, dot till 1. And in this case, there would be three different segments of length 1. That's kind of how the pattern goes. And so, yeah, that's kind of how it increases by this amount. And so a simple for loop, that's in the editorial, by the way, would be like 1 to n, and your answer, it's a pseudocode, and plus equals to, why do I keep doing that? Plus equals to plus run. Run would equal to 0. And then, oh, actually I did this wrong. If AI, which is, let's just say this is A, I equals to 100 and plus equals to plus run, else run equals to 0. So if I encounter 0, this ends and we have to restart all over again. And the reason why this works is because let's just go through this segment, right? It'll be so run equals to 0, and then it changes to 1 because it's prefix addition, so it'll be 1, and then you would add 2 to answer, and then you would add 3 to answer, and this is just like this. It's the same formula, so it works. This is also in the editorial if you want to peek at it. Let me just really quickly pop it up. Yeah, so this is what this means. They make it a little complicated, I feel like, but it's okay. So yeah, they just add that. And so the next step after this is to add numbers other than 100 and 0, right? Let's add like a nice little 150 in the middle of this segment of 3. And this is kind of where complementary counting comes into handy. So if you didn't understand that earlier, you're going to understand a little bit better here. So you'll notice that instead of a total of 8, wait, this had 8, right? 1 plus this would be 6. Yeah, this one had 8. This had 8 total. This is going to have a total of I think it's 7. Yeah. Actually, I need to put 7 after I undo all these. Put 7. And this is because, if you notice what I was doing, is because I skipped circling this 150 because the minimum of just 150 is not equal to exactly 100. And that really pissed me off. It's exactly 100. Yeah, and that was pretty tough, but it's okay. Harder the problem, the more you learn, if you know what I mean. So how do you do this? This formula, what we did earlier, the pseudocode doesn't work either. So what we do is complementary counting. So we just basically take this for loop, right? And we say it's greater than or equal to 100. Or greater than or equal to 101. And plus equals to plus run. Same idea, int ands and run starts at 0. Same idea, else run equals to 0. Same idea. And the idea is it will only find this guy one segment because this is the only segment that's greater than or equal to 100. And it'll find the total, I guess, like number of pairs within that segment, and that would be 1, right? So keep that number in mind. And from here, we're going to also update how we're going to count the hundreds as well. And instead of equal to 100, it's also going to be greater than or equal to 100. And so you may be like screaming at me. This has an S, by the way. You may be screaming at me and you're wondering, hey David, this also counts the 150 as well this way because it also counts it as part of the segment. Well, that's okay, right? And what you're going to end up with is also 8, okay? But what you'll do is it's going to be 8 minus the number of segments and pairs that are greater than or equal to 100, and that will help you get the total amount. Boom, kind of crazy. Boom, this is my brain. But it's pretty crazy. I thought this was a really cool idea. I knew complementary counting before, but this was a very interesting way to put it. And I think USACO problems always have like one of the best problems ever. They probably have one, if not the best problems. Now, how are we going to convert this into 2D, right? Because with 2D, right, let's say I add another array, maybe like, right, and what's gonna happen is you're gonna have rectangles like this in all 4 cardinal directions, and it's gonna be crazy. So the Editorial has multiple solutions. One's in Java because I can't read. Oh, I know Java, but it's just like unreadable to me. But yeah, this one's also pretty interesting too. Oh wait, yeah. But I think the best one would be this one. I think this binary one. And there's also an O of n squared time too. I don't really understand it. I think it has the same concept. Could be interesting to read. I'll maybe check it out later. But the idea is, so they make a boolean of OK. And so OK differs, but actually, let me just quickly review this so I can make sure I'm not saying anything stupid. What would be all ones? All ones is true. Okay, I think I get it. Wait, all ones K. K. Okay, so that's the same idea here. What's gonna happen is let's take back the example of 0, 100, 0, 100, 100, 100, and I think I changed it up a little bit, but it's okay. And then we'll make another part. Maybe add a 150 in there. Just actually, we'll make it just hundreds for a second, so it'll be easier to process. Right, we'll just make it like this, even though it's probably never going to be this size. Yeah, actually, you know what? Screw it. I'm going to make it just 3 by 3. It makes the same example, it just saves time. Okay, so this is A. Okay, so what you do is you would do the same formula we did here to the left, this guy right here, and apply it to every single segment. So, yeah, in this case, it would be like, actually, yeah. So 0, yeah. So let me introduce the Boolean array OK. So OK, it's just a Boolean array, and it's gonna mean multiple things, but at first it's gonna be whether a I j is greater than equal to 100. Okay. I'm gonna move this over here. And so this is no, it's not. Yes, it is. Yes, yes, no. Yes, yes, no. And so now, okay. Now, So now we're going to do another array. It's going to be called all ones. And this is going to be, at first it's just going to be, it's a 1D. It's going to be all ones, like this. And so it's going to be all true at first. Let me just check. And yeah, upper row I to lower j. 0 I, it'll go down the row. All ones I, go down the row, but wait, why isn't this j? Okay, sorry about that. But all ones would be like this, and so we'll use the and. We'll use binary, so and what this would do is whether if there's two ones, it's true, and then everything else is false. Okay, and so what this would help us do is, what we can do is we'll loop, so we'll have two loops, right? One, this would be I, 1 to n, j, 1 to n, and these will be the starting and ending spots to your rectangle. And so it'll just loop through all of these. So you'll loop through, let's start to that actually. All of these, and so what you'll and it all. So at this first loop, all ones will change from this to 0, 1, 0. And yeah, and then you'll do this to k. Let's see, k, and okay. Yeah, if all ones k. Okay. So you'll loop through all of these guys, and if there is a 1, right, you add to the run. So you add to the run. So let's say run starts at 0, and now it becomes 1, right? Then, yeah. So this will help. So without this second loop, right, you're just going to be counting every single row, if that makes sense. And you'll count the number in 1D fashion. Now with this second j, right, what it helps us calculate is this. So let's say we go, and this is the starting point I'm going to change colors actually, it's getting hard to read. I'll start I here, and j here, and we'll and it again. So instead of starting with 1, 1, 1, what's going to happen is it's going to change to, it's going to change to 0, 1, 0 again. Actually, it doesn't change, but you'll see that 1 ends with this, and it's good, and 0 ends with 1, changing from this 1 to 0. If you don't know what and is, just like read up on it. But what this helps us do is we can find rectangles, or we can find 2D rectangles because it adds this 2D element to it. So if they're both and, that means both are good, right? And so run also equals to 0 every time. So this would only add to 1. So run would change back to 0, and then now it's 1 again. So it adds one more rectangle to your answer. Now another cool thing is, let's just switch it up for a second and change these guys. Actually, wait, I only have to change one actually. Change, please. Gosh. Let's just change this guy to a 1, right? And in doing so, what it would do is these two become 1s. And now with the run, right, idea, what starts as just adding 1, you can add 1 plus 2 because, run updates. and this gives you 3 rectangles, which is kind of cool. Yeah, so it gives you 3 rectangles, and 3 rectangles would be 3, or actually it would be just 1, 2, wait, I think it's the 3 comes from something else I remember. Oh, it could be 4 if I'm correct. Oh yeah, it's this. It's 3 rectangles, and then this guy, this rectangle here is counted when you do 1D operations. So when I equals to j and I equals to 2, or not j equals to 2. This is when you count 1D. So if it's on the same row, it's counted 1D. And also these singular ones too are also counted when you do just 1D. So yeah, it was very hard to explain. Wow. But yeah, and I kind of like this binary one because it's kind of cool, and you don't really you see binary a lot more than you would realize. And I really don't want anyone to be scared of binary because it's just so weird, but I think people will like it. And so yeah. Oh, I forgot to add this too. So you'll take this and greater than 100, right? But you'll also notice that if, like, let's say we'll change this guy to 150, right? It's gonna count this as a rectangle. So we'll have to do the same strategy what we did here. It's for complementary counting, and we'll change OK to whether aij is greater than 101, and then subtract that from the answer to answer 2. Answer 2 would be the same formula, but whether if OK is a different form. So yeah. Let's just change to what's good enough. So, don't mind fit. This fit doesn't matter, actually. I'll zoom in, actually. I know how, like, tutorials get, like, really hard to read. Yeah, this is a good length. So let me just close my compiler. So, this is just input right here. This does not matter, actually. Yeah, don't mind this. Input. Okay, so this is the first part. Whether OK is the value is greater than or equal to 100. And so, yeah, that doesn't matter either. Yeah, and then we basically did the same thing with the editorial, just good, and they're all equal to 1. And this way it counts both 2D and 1D areas. So if j equals to I, it's going to count 1D. And if j is greater than I, it's going to count all those 2D rectangles. Remember, if 1 is still there, that means there's going to be a contiguous area right here. So yeah. Yeah, and then you end the run when it's not good. Then you calculate the second part, which is here. If it's just greater than, strictly greater than 100, same idea here. This is just copy-paste code. I could have just did what the editorial did, and I think they made a function, which is a lot more useful. But yeah, wrong thing. Yeah, so it's greater than 100, and then I just output it. And right here, instead of adding it, I just subtract it. Yeah. So this problem was definitely a handful. I had a lot of fun with it, though. It was a lot of struggling, but I learned a lot of cool things about it, and I actually really enjoyed explaining it to y'all. So, yeah, this is definitely one of the harder ones. Definitely one of the harder ones. This could be even, whatever. I was going to say gold, but it requires a lot of thinking. So, some of the guys use prefix sums, a lot of weird stuff that I think, like, they use prefix sums to calculate all at once, but yeah. So yeah, EC or accepted, and yeah, I think that is the end of February. Hopefully y'all enjoyed, and I'll see you next time. I'll probably do January too.